Hi folks, this is Matt Ingram again, continuing the replication of Baller et al. In R. I assume several preliminaries at this late stage in the replication of Baller et al. No prior knowledge. I assume that you know about this reference to Ansel in 2007, that you've downloaded and installed the software, that you have access to the data, and that you're already familiar with the R environment. And I'll start right here with replicating table 3 and then move on to table 4. So let's shift over to R. In the R environment, um, we basically want to replicate table 3 in Baller et al., which is here on the right. And Baller et al. Tell us that we've already worked through the spatial chow test and detecting different regimes and the coefficient instability, and we've done a general Lagrange set of tests, a set of Lagrange multiplier tests on the OLS regression of the full data. But here, before we do the spatial lag regression in the south, I'd like to do the Lagrange multiplier test again, just for the southern part, the southern counties of the US. So we'll load just the southern counties using this command for the shapefile. Hang on just one second. Okay, so I've just checked the working directory. I've reset it to the working directory. And I'm going to load the shapefile of the southern counties. See it load there. Move down in the R script. We could summarize it, but just let's attach the data frame so we can work with it. We'll create a new row standardized spatial weights matrix of the 10 nearest neighbors just for the southern set of counties. And we'll make it symmetric and a list object. As you'll recall, almost all of the spatial commands in R require a list object. We could generate several list objects just in case you have. I would just create this generic command making the list object whatever it is, whatever the spatial weights matrix is that you are using, so that you don't have to change all of the commands below. And now something that Baller et al. Don't report directly, we're going to run the linear regression again just for the southern counties. Again, you can see that we're using the NatS data set, the data frame that we just created above, using only the southern counties. We'll run that, and then let's run the Lagrange multiplier tests on the residuals of that least squares regression object. Here they are on the left. You see the basic error test is large and statistically significant. The basic lag test is also large and statistically significant. The robust version of the error test, however, is not statistically significant, and the robust version of the lag test is statistically significant. So this indicates that we do want the lag specification, as Baller et al. Indicated, in the southern counties. However, the mixed test remains statistically significant just as it was with the full data set. So this is an unresolved point, unresolved even in Baller et al., and we might actually want to specify a different kind of model in the southern counties. Let's set that aside for a moment and just go on with the replication, and let's replicate the spatial lag model of the 1960 homicide rate in the southern counties. So this is the full command. This is the specific command, lag spatial autoregressive linear model, lag SARLM. Again, you could use any of the help or search commands to look up more syntax or descriptions of this command. But we're going to create a new object, SLM60, using that command on our dependent variable, our independent variables, using this data, our spatial weights matrix, and we're going to use this method. The default is eigen, but it takes a long time. So just to make things faster here, I'm going to use this option matrix. So let's run this command. Excuse me. And I'll come back in just a second. Okay, so here we are again. Our command has executed, and let's summarize the object that was created. Here we see our results, our predictors, and here is row, reported, and statistically significant. Let's compare that with the output in Baller et al. Excuse me, let's just clear this up a little bit. So here's resource deprivation 1960, and you can see that in 1960, 0.832. Hang on just one second, it doesn't look like it's... Well, as you can see, there are some differences in the magnitude or the size of the coefficients, but let's just keep looking through them and see if there are any major departures. For resource deprivation, it's positive and statistically significant. Our results are positive and statistically significant. Population structure, Baller et al. Reported non-significant. We also find non-significant. For median age, Baller et al. Find negative and non-significant. We also find negative and non-significant. For divorce, they found positive and significant. We also find positive and statistically significant. For unemployment, they find not significant. The direction is negative. We found negative and significant. So this is a difference. Again, as you might recall, we also found some differences on unemployment in some of the other models that we ran in Geoda. This is the coefficient for row, as I mentioned briefly just a minute ago. Here is row in Baller et al. Again, positive and statistically significant. So let's return to our script. We could summarize this regression object. Again, we could create a new object of the summary and output that as a CSV file, just as we did before. We could run a Moran test on the residuals. We see that it's no longer statistically significant. This is a first indication that we've accounted for the spatial autocorrelation in this particular model with the inclusion of a spatial lag. So that's a nice result. So one exercise that you could do with this code here is replicate the remaining findings in Table 3 for 1970, 1980, and 1990. As before, you could also combine them into a single file and export that in CSV or some other format. Let's take a look now at the spatial error regression in the non-southern counties. So in the non-southern counties, to examine that spatial error model in the non-southern counties, let's load the non-southern shapefile. You can see it load here on the left successfully. Let's create the data frame and attach that data now. Excuse me. Let's create our new weights for the non-south. Creating our 10 nearest neighbors spatial weights matrix. Let's make that symmetric and make it a list object, and then select that with our generic identifier list _w. We could now run, Baller et al. Don't report this, but we could run now least squares model just on the non-southern counties to see what the results are. You can see we're calling this OLS 60 non-south linear model, and we're using the data that we just created, this data frame that we just created, nat_ns.data. So again, let's run this. You can see it successfully ran there, and then let's run the full set of Lagrange multiplier tests on this new object that we just created. Here are the results on the left, and you can see that the basic error test is statistically significant. The basic lag test is also statistically significant. Now we have to move then to the robust versions of both tests. The robust version is not of the error test is not statistically significant, and the robust version of the lag test is statistically significant. So by this diagnostic, it's not entirely clear why one would want to run the spatial error model only on the non-southern counties. If anything, it looks like one would want to run the spatial lag model as well on the non-southern counties. And if we look at the mixed model, we see that it remains statistically significant. So again, there's an indication that there's some sort of mixed spatial process underlying the data in the non-south, just as we saw in the southern counties. If anything, there's a spatial lag process underlying the data in both the southern and non-southern regions, but there appears to be more of a mixed process. In any case, let's move forward with the replication of the spatial error model in the non-south. Did I lose my spot here? Give me just 1 second. Okay, we're back, and as I was saying, let's just move ahead with the spatial error model in the non-south. Just to stick with the structure of Table 4 in Baller et al., here's the spatial lag model of 1960. Actually, I stand corrected from what I just said. I just remembered that it was indeed, as they said, that there was a spatial lag process in 1960, not a spatial error process. That's what they modeled in the first set of results in Table 4. Let's repeat this OLS process for 1970. I'll write up the code here and then repeat the model in just 1 second. So here we are back again. As I mentioned, I stand corrected that we actually just replicated the first model in Table 4, which was the spatial lag process. Baller et al. Identified that spatial lag process. Let's move to the first spatial error process that they examined. That's in 1970. So let's just repeat exactly what we just did now. We're going to run an OLS regression on the non-southern data for 1970. Let's do our full set of Lagrange multiplier tests. Here are our results. Here's the basic error test. It's statistically significant. The basic lag test is significant. We move to the robust version of both. The error test is significant, and the lag test is no longer significant. So now we're right on track, replicating exactly what Baller et al. Found. There does still remain some evidence of a mixed process, as there was in the southern counties. But again, let's set that aside for a moment and just move on with the replication of the spatial error process. So this, excuse me, is the spatial error model of homicide rates in 1970 in the non-south. This is the command error spatial autoregressive linear model. We've got our new object being created, spatial error model 70 non-south, from the following commands. Again, the default method is the eigen or eigenvalue method, eigenvalue decomposition method, but let's use this matrix method since it's much faster. So I'm going to run this model, and our results are complete. Let's summarize this model and compare it to the results for Baller 1970. So there's our intercept at 6.21. There's your intercept here, 6.16. It's approximately the same. Resource deprivation, 3.03. Resource deprivation up here, approximately 3, but it's positive and statistically significant. Population structure is positive and statistically significant, approximately 0.8. We get the same result here, 0.859, 856. a median age is negative and statistically significant, we get the same result here, negative and statistically significant, and also the magnitude of the coefficient is approximately the same. Divorce is positive and statistically significant. We also get the same result, and the magnitude of the coefficient is approximately the same. And unemployment, they find, is not statistically significant. We generate the same result. The result for unemployment 1970 is non-significant. Now, lambda, in this first spatial error model, the coefficient, the magnitude is 0.24. We've got 0.25 and statistically significant. As we mentioned before in the Giota replication, we don't see the statistical significance here for lambda, but we've replicated the basic result here. Let's move back to the R script. So one exercise you could do to continue this replication is to replicate the remaining results in table 4. That would be the spatial error model for 1980 and 1990. You could then combine all of these results into a single file. One thing that I didn't report just now is we could do a Moran test as we did before for the spatial error model. Let's do that. And we see here that it's no longer statistically significant. That means that our spatial error model has accounted for the spatial autocorrelation in the data. So that's a nice result. Again, you could do the remaining replications and then aggregate all of your results into a single file and output that in various formats. So that's the complete replication of Baller in R after having done it in Giota in the first set of videos. I hope you find this useful and continue with the remaining replications. Thank you.